Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to give an example of how to apply integration by parts. So what we're looking at here, we're going to try to figure out the integral 0 to root 2 over 2 of the product 2x inverse sine of x squared dx. Always want to take a minute and talk about big picture things. There's several different integration techniques. Integration by parts is used when you see product of two functions that don't look alike. So here we have an algebraic function and here we have an inverse trig function. That's our clue that integration by parts are going to be our method of choice here. First thing you do when you're using integration by parts is you choose the value for u, and then whatever's left is dv. I always do this based on Lie 8, which if you've seen my previous videos, we know what these things stand for. Logarithmic, inverse trig, algebraic, trigonometric, exponential. This is what we use to choose our u's. Been using that thing for 25 years. It's never failed me yet. All right, so I look through your logarithmic. I look at my function. I don't see a logarithmic function. Next on the list, inverse trig. I look right there as an inverse trig function. So based on this, the u we're going to want to choose is inverse sine of x squared. So, I don't need this anymore. Alright, so our u, inverse sine of x squared. Whatever's left is your dv. That's going to be 2x dx. Then we're going to calculate du and v. I'm going to do the v first because it's the easiest. Antiderivative of 2x squared dx is x squared. I'm sorry, I thought I talked ahead there. Antiderivative of 2x dx is x squared. Now the du, we're going to have to differentiate this inverse trig function. So what I'm going to do is I'm going to take a moment and do that off to the side. All right, so let's say y is equal to the inverse sine of x squared. Then sine of y is equal to x squared. Now, if we implicitly differentiate this, this is going to read cosine y times y prime is equal to 2x. So y prime is equal to 2x over cosine y. Now we have to deal with the cosine y part. We do that from this. I'm going to make a little triangle. Here's an angle y. And because sine y is equal to x squared, the dimensions of this triangle, let's see, this would be an x squared. This is a 1. Because sine is opposite over hypotenuse. And if I wanted to, I could write this x squared over 1. That makes this distance equal to the square. Ooh, I'm going to take a moment here, call it d, and actually write out Pythagorean Theorem and be kind of careful with this, where d squared plus x squared squared is equal to 1 squared. So this d here is equal to the square root of 1 minus x to the 4th. Right. Now getting back to why we were doing this, because we needed this cosine y. Cosine y would be adjacent over hypotenuse, so that's going to be square root of 1 minus x squared over 1. If we divide by cosine y, that is going to equal, let's see, we're dividing by this over this. So that's going to give us a square root 1 minus x to the 4th in the bottom. I'm going to take a moment to make sure that's right. So cosine y is equal to this over this. All right. So what I've just found here, if this is my u, then my du is equal to 2x over square root of 1 minus x to the 4th times dx. I'm going to just kind of take a minute here and pause this. little siesta here, so I need a little more room on the screen. So I'm going to get rid of this stuff I don't need anymore. All right. So our integral here, and I'm just going to use this symbol here to represent this integral, is equal to, by the integration by parts formula, uv minus integral v du. So that's going to equal x squared inverse sine of x squared evaluated from 0 to root 2 over 2. This is a definite integral, so it has bounds. Minus the integral of v du, so that's going to be minus the integral of x squared times 2x dx over square root 1 minus x to the 4th. This integral also from 0 to root 2 over 2. Okay. So integration of parts. uv minus integral v du. So that's going to be this product. Right? That's where this term's coming from. Minus the integral of this product. I'm going to take a moment here and just reflect. Everything look good? All right. Let's start thinking about this thing now. So this is going to equal, now, root 2 over 2 squared is going to give us 2 over 4, I believe, times the inverse sine of 1/2. By time we take the 2 over 4 and square it, minus 0. I'm going to put this in brackets. So this is just the evaluation of this antiderivative at these boundary conditions. Minus integral. Now let's see, this 2, why don't we bring that out in front? Then we're left with integral x to the 3rd dx over square root 1 minus x to the 4th. And again, this is from 0 to root 2 over 2. Now, this was a definite integral, so this had limits, which means I don't need to worry about tacking a constant on. I'm going to go back and work on this a little bit more here. So this is equal to 1/2 times the inverse sine of 1/2. Now the inverse sine function, a little reminder about the inverse sine function. Inverse sine function is defined from minus pi over 2 to plus pi over 2. So this is the angle that has a sine of 1/2. That's between minus pi over 2 and plus pi over 2, and that is pi over 6. And then minus 0 for that 0 right there. Okay. Minus, okay, again, working on this guy, twice integral 0 to root 2 over 2 x cubed over square root 1 minus x to the 4th dx. Kind of separate this off here. Okay. Next, this integral needs to be worked out. Integral x to the 3rd over square root 1 minus x to the 4th from 0 to root 2 over 2. I'm running out of room, so I have to erase some stuff. I'm going to take a moment here and just ask for any questions before I do start erasing things. All right, I'm back here, so let's see. I need to clean up and get myself some space here. So I think what I'm going to do is write down here OI, which stands for original integral, is equal to pi over 12, by the time we simplify this, minus 2 times the integral from 0 to root 2 over 2 of x cubed over 1 minus x to the 4th square root dx. I'm keeping this here now, and what I'm going to do is get rid of some of this other stuff to make myself some room. Oops. Okay, so What I'm going to do now, and I'm just going to circle this in red, is work on this. And because I like to work down, I'm going to take this whole thing, move it here. All right. So now, focusing on the integral in red. I'm going to do this by substitution here. I'm noticing that if I differentiate 1 minus x to the fourth, its derivative, you're going to end up with 4x to the third, basically to within a constant sitting right here. So the substitution we're going to want to work this integral is going to be, whoops, here, so I'll go ahead and do this in red. Let u equal 1 minus x to the fourth. Du would then be minus 4x cubed dx. If x is equal to 0, u would equal 1. If I put a 0 right here. If x is equal to root 2 over 2, u is equal to, oh boy, I have to write that out, 1 minus root 2 over 2 to the fourth, which is going to equal 1 minus, let's see, root 2 to the fourth power is 4, I believe. And 2 to the fourth is 16. So it's going to be 1 minus 1/4, which is 3/4. You guys, everybody following along? All right. So now, the integral in red, I'm just going to do this, code it here. So this integral I've circled in red is equal to integral from 1 to 3/4 square root of 1 minus x to the fourth can be written as square root of u. I'm going to look right here now, minus 4x to the third dx. Now I don't have a minus 4 here, but it's a pretty easy fix. I'm just going to put a minus 4. And somewhere else divide by minus 4. Doesn't matter where. Minus 4x to the third dx, minus 4x to the third dx. That's now equal to du. But I've got that minus 4. I'm going to put that right there. And again, it doesn't matter if that's brought out in front of the integral or not. It doesn't matter where you put that. Okay. This is going to equal minus 1/4. All right, now, this is the integral of du over square root u. This is u to the 1 minus 1/2. So when we take the antiderivative, that's going to be u to the positive 1/2. Divide by our new power. That's going to be the same as multiplying by 1. And that's evaluated from 1 to 3/4. Whoops, that's getting hard to read. 1 to 3 over 4. That's still hard to read. I'm going to write it right here. Minus 1 over 4, u to the 1/2 times 2 over 1, and that's all evaluated from 1 to 3/4. Right, needing a little more room. I'm going to get rid of this. All right, so we're going to evaluate this integral now. Okay, let's start with the constants. 2 over 4 is 1/2. I'm going to go ahead and take this minus sign and absorb this into the limits. So I'm going to evaluate this at 1 first. Square root of 1 is 1. Minus, now we'll evaluate it at 3/4. So that's going to give us a root 3 over 2 by the time we square root it. I think I'm ready to put this whole thing together now. So, our original integral is equal to, we got this pi over 12 sitting here, minus 2 times the integral in red. I'll put this in brackets, which we have just worked out to be 1/2 times 1 minus root 3 over 2. I'll go ahead and do one more simplification. For those of you who know me, you know that I think simplification is kind of overrated, but I'm going to go ahead and multiply this out. That's going to become a minus 1. And then when I distribute to this, and then to this, plus root 3 over 2. I'm going to just kind of double check that. Minus 1 times 1 is minus 1, and minus 1 times minus root 3 over 2 is plus root 3 over 2. I'm going to call that done. There's a numerical value of the definite integral from the beginning of the problem. So, I hope this video helps demonstrate how to work these. Have a great day.